We're very happy to have the picture language seminar start today with Seth Lloyd. Seth Lloyd is an expert on algorithms. He invented so many of them. And today he's going to talk about algorithms for computing homology. So Seth, we're looking forward.
Great, thank you. Can people, will you people hear me via the microphone there? Yes, good. Yeah, right, today I'm going to talk about quantum algorithms for computing homology. And let me just get this so we can see it. There are several reasons for doing this. One is just it's kind of cool. These are algorithms. They started off with work that I did with Paolo Zanardi and Silvano Guardarone a few years ago, and now we're continuing this with Sasha Schmidhuber, Michelle Riley, and Paolo and Aaron. What's Aaron's last name? Lauda. Aaron Lauda, the head of the math department at USC. We're working on algorithms for Khovanov homology, and so it's when people think of quantum algorithms, they think of algorithms for things like factoring and code breaking, and then for things like quantum simulation and for machine learning. But these algorithms for homology, algorithm for algebraic topology.
The Blackboard light.
Oh, everything okay?
The Blackboard light, not the room light.
Just press that.
Great. So these are really algorithms for kind of pure math.
Can we turn on the room light?
Actually,
You guys work on this while I keep talking.
Yeah.
So these are algorithms for pure math, and we're also working with here with Bobak, Kiani, and Melanie. What's Melanie's last name?
Weber.
I'm sorry? Weber. And Melanie Weber on applying these algorithms to algebraic topology, sorry, to algebraic geometry as well. And I'm going to tell you about the kind of central quantum algorithm that kind of underlies all of these methods, which is this algorithm for doing homology today. And homology. Let me just check here. How many people come from a quantum information kind of background here? Right. How many people come from a math kind of background here? Right. Okay. Some people seem to be in a superposition of both. Right. So what's going to happen in terms of the order of this talk is first I'm going to talk a bit to introduce the whole notion of homology and algebraic topology for people who maybe don't know about it, as I did not when I began working on this in this field. And so there was a kind of a high bar to entry. And then having done that, oh, hi, there you are, Melanie. Sorry, excuse me. My apologies. And having done that, then I will show why these are very natural algorithms to which to apply, very natural procedures to which to apply quantum algorithms. And I'll describe these algorithms, and I'll describe some of the work that we've done and that we're continuing to do. And welcome everybody to try to come up with cool new stuff to do this, right? Because actually, homology, for those who know about it, is a tremendously powerful tool. It was really that it started off very early in the study of topology, in conversations between Riemann and Betti in the 1860s and 1870s, and then Poincaré made some really great breakthroughs in the 1890s. And then the kind of contemporary version or modern version of homology was really developed by Emmy Noether and Vitoris in the 1920s. Emmy Noether being, of course, physicist's favorite mathematician. When I go to the Royal Society mansion in Buckinghamshire, I always ask for the Emmy Noether room. Which happens actually to have a secret bathroom. I mean, it's like the bathroom is hidden. There's a secret bookshelves. It was like if you arrive late at night, it's good to know this. But yes, it took me a long time to find it. You open up a bookshelf and it's behind the bookshelf. All right. Good. So, yeah, sorry, that was somewhat irrelevant. Here I'm showing, here's a torus. It's topologically non-trivial. It has two non-trivial cycles that can't be deformed into each other. And one of the goals of homology is to figure out what's going on with such systems. So it's a fundamental method for calculating topological invariance. Actually, it really began with Euler and the Euler characteristic and the bridges of Königsberg problem. Via Riemann, Betti, Poincaré, Noether, Vittoris, and Meyer. And here, we started off with looking at surfaces of different genus and with different numbers of holes and voids. Poincaré showed how you could look at simplicial discretizations of these surfaces and then calculate homology from that. And the contemporary version, is there a pointer? Yes, there is. Yeah. The contemporary version describes this in terms of chain complexes, which are chain complex. Each of these is an abelian group, and then these decays are maps from along this whole series of abelian groups. These are called boundary maps, and we'll see what their properties are in just a second. See, the origins of this are to count the number of connected components, holes, and voids in high-dimensional systems. But now there's a wide set of applications in pure and applied mathematics and data science. At the end of this talk, if I have time, I'll mention briefly the work that Sasha, Aaron, Paulo, Michelle, and I are doing on Khovanov homology, which is a way to look at knot invariance in terms of homology. So it's a powerful set of techniques. So now I'll go, so are there any questions about that? That's the end of the introduction. Yeah.
So does the way its isolation matters, like what we use?
Yeah, so here we go. We have each of these. The way we do the calculation does matter, and it turns out that the calculations you do in order to calculate homology turn out to be eminently suitable for doing on a quantum computer. In the abstract, these are just a whole tower of abelian groups with maps between them, such that if I apply this map twice, so first I go apply this map from dk plus 1, we'll call it the boundary map here. It maps a simplex to its boundaries, or like a chain of simplices to the boundaries of this chain of simplex. And then if you apply it again to the lower dimensional boundary, you find that it's 0. So the boundary of a boundary is 0, as the quote goes. So for example, here's the boundary map D1. So this is acting on a one-dimensional simplex, which is an edge made by 1 and 2. And the boundary map here ends up being 1 minus 2, where these are just points. So they're zero-dimensional simplices. And the signs are important here. So very important to keep track of signs throughout. We'll come back to that again and again. And so here you see that here is a sequence like this, a chain of these simplices going around. And these dots are just these edges. So this is a one-dimensional chain. And then it gets mapped to the zero-dimensional points on its boundary, which is 1 minus 2 plus 2 minus 3 plus 3 minus 4 plus 4 minus 1, and that's equal to 0. And that's why these, if you keep track of the signs for these simplices, the same boundaries of a boundary being 0 works out in any dimensions as well. So it's easier to visualize in a small number of dimensions. Okay. So let's look at the simplicial, also called singular homology, which was this innovation of Poincaré's from 1896. Then we'll see right away about how we're going to represent this quantum mechanically, which comes to your question. So we're going to set things up in a way where how we do the computation is, it's going to be done by a quantum computer.
So actually what I mean is that, so you're using like it's the triangle and you square and other shapes.
Yeah, so actually this method, sorry, let me go back. So these are, this method applies generally to any situation where you have a chain complex. So these chain complexes were developed. I think the idea was developed by Noether and Vittoris and Meyer in the 1920s. And then it's a very general feature. It goes way far beyond just having, simplicial homology. There are many kinds of homology. So for instance, if you're familiar with like cell complexes like CW complexes, those are also can be described by chain complexes. And in fact, many structures just, just like out there in the universe that do not on the face of it have anything to do with, geometric or topological shapes can be described by chain complexes. So this method, as Sasha and I showed in our most recent paper on this, can be applied to any chain complex, subject to restrictions on whether you're able to encode the features of the chain complex into a quantum computer. In particular, can you do have access to these boundary maps here?
But will you explain to us why a quantum computer does it better?
Oh, yeah, for sure. Not if you keep asking all these good questions. Sure, absolutely. And we'll do this right now. So here's a zero simplex. Let's just look at this simplicial homology. This is a zero simplex, it's just a point. One simplex is an edge, a two simplex is a triangle, three simplex is a tetrahedron, etc. And if I have n possible n points, then there are n choose k plus one possible k simplices. Because say a one simplex has 2 points on it, a two simplex has 3 points in it. And then the total number of possible simplices is 2 to the n, which is just the dimension of the power set of this set of points. And the way that it's going to work, just like to give you a taste of it, since you were asking, I will explain it in greater detail later, just give a taste of it, is that the abelian group we're going to use is C to the 2 to the n. So each simplex is going to be a map to member of the abelian group, but the abelian group is just going to be the vector space, complex vector space over n qubits, which is dimension 2 to the n. And this makes everything quite simple and straightforward in terms of mapping these things to mapping simplices to qubits. And here I've expressed this in this way. Here's a representation where I'm going to map the state 1, 2, 4 in this. There are 4 points in this set, the simplicial complex. There's only 1, 2 simplex, and this maps to something that labels the vertices of this simplex. So 1, 2, 4, and this is just a quantum state. And there are multiple ways to encode this, but you can imagine anything you want. Another way to do it is you simply, there are n qubits, k simplex is a set of k plus 1 vertices that are fully connected, and you just put ones at the places where those in your state, at the places where those vertices are, and zeros elsewhere. It's an equivalent way of doing this. Or you can just write it as a list like this. So these will be quantum states, and then our boundary maps will end up being a set of sparse linear operators on this very high dimensional vector space. And here we go. So this is how it works. So you see I've immediately gone into using this quantum notation. And we'll talk about how to construct these quantum states in a bit. But the idea here is that the boundary map is you map, if I have a k simplex, which is a set of k plus 1 points, I map it to the alternating sum of the k minus 1 simplices on the boundary. So first I omit the first vertex, and then I omit the second vertex with a minus sign, and then the third vertex with a plus sign, and the fourth vertex with a minus sign, etc. So I map this into the sum of the alternating sum of these quantum states corresponding to the simplices on the boundary, where this little hat means I omit that. Is this clear? Right, and these minus signs, of course, are very important for, as we saw, for the boundary of a boundary being 0. It takes place with orientation of these simplices. We have to keep track of the orientation of these simplices, and the minus signs then mean that all the math goes through the way it should. So, for example, here is the D2, which acts on the 2 simplexes. Here's the simplex 1, 2, 3, and that's equal to 2, 3, where I omitted the 1, minus 1, 3, where I omitted the 2, plus 1, 2, where I omitted the 3.
Seth?
Yeah.
So on each k simplex, you put a qubit here.
Right. So the idea is there are 2 to the n possible simplices. Well, this is one encoding the simplest encoding, really. Is that you have a simplex, there are n vertices in the complex. And then there are 2 to the n choose sorry, there are n choose k plus 1 possible k simplices. So you can either list the labels of them, which is what I did the first time, or I just described verbally. You can have, you know, a 1 where there's a vertex and a 0 where there's not. I'm sorry, I should have written that other alternative code. But there's a lot of flexibility in terms of how you code things as long as you keep track of these minus signs. Okay, so for example, just to show you how this boundary map works, here's a chain, which is I've got it's made up of 2 simplices, 1, 2, 4, 2, 3, 4, and they share this edge 2, 4. And the way this works is I write this as the sum of this. I left off these ket vectors right here, but I write this as the sum of this vector plus this vector. And now I take the boundary, and the boundary of this is just 2, 4 minus 1, 4 plus 1, 2. And the boundary of this is just 4, 3 minus 2, 4 plus 2, 3. And you see that 2, 4, the interior edge or interior face, occurs twice with opposite signs, so it just goes away. And I'm left with this boundary, which still has signs attached to it, which is 1, 2 plus 2, 3 plus 3, 4 minus 1, 4. Yes.
Sorry, I still think I have a question about notation related to the previous question. So you showed that the simplex, the two simplex 1, 2, 4, you wrote it as the vector ket 1, 2, 4. Should I interpret that as saying I'm putting on the qubits? So if I were to express this in terms of notation of qubits, I would write 1, 1, 0, 1.
Yeah, you could write it. You could either write it as something like this, you know, 1, 2, 4, right? Which would just be a list of the labels.
Right.
Or another way to do this would I put a 1 where there's a vertex, so it would be 1, 1, 0, 1. So that's because 1 is in it, 2 is in it, 3 is not in it, and 1 and 4 is in it. So these are alternative ways of doing this. If you do it this way, it's slightly less slightly less efficient, but it's easier to keep track of the signs. So both of them work fine. Great. Okay, great. All right, so any more questions about this? I mean, this is when Paolo and I first tried this, our friend Mario Rossetti, the head of the Institute for Scientific Interchange in Torino, suggested we do this in the context of what's called persistent homology, which is a machine learning technique to learn the homology data. And we started trying to read the papers. And since I didn't know anything about algebraic topology, it didn't make any sense to me whatsoever. And the papers were like hard to understand. And so we failed. And then 3 years later, we tried to read the papers again, and then we failed again. And then 3 years later, we were at the Physics Institute in Banasque for a month. And we said, after breakfast, we're going to sit down and we're going to try to understand this. And we're not going to, you know, we're going to continue doing this every day until we figured it out. And then once we realized, I think Paolo knew a lot more about the simplicial homology than I did. But once we kind of figured this out, then it's okay, fine, we can just, this is the mapping, we can do it. And it's quite a straightforward mapping, actually.
So
Yeah.
is there any advantage to thinking of not using 2 states, but qubit states with more than 2 values?
Yeah, absolutely. Though it will just be, the advantage will only be linear in the number of qubits, right? Because
But can you capture some other phenomenon in the homology or
that's a
cohomology?
good question. And you know, you mentioned that I developed a lot of quantum algorithms, but in fact, possibly my main or earlier claim to fame with quantum computing was showing how you build quantum computers, you know, with multiple with systems that are interacting atoms or quantum dots, and you zap them with light and you see how they behave. And you know, in actual real quantum computers these days, you frequently have qubits for free. So for example, in superconducting qubits like transpons, then you have multiple levels there, and actually, if you don't access them, they're kind of a pain, because stuff gets, lost at these levels, and it's a source of noise. So that would be great. Actually, an entertaining possibility, which I don't think any of us working on this together yet have even talked about, is maybe we could use infinite dimensional systems like oscillators, like harmonic oscillators, to do this. And there are lots of harmonic oscillators are great physically. They're the most coherent systems. You need some kind of nonlinearity to address them, but maybe that would be a cool thing to do.
And you've worked on them too.
Yeah, exactly. And I even know about it, right? So that's why I work. I like, I don't look under the lamppost. I have my own little headlamp, and I look where my headlamp is there. So that my headlamp points in that direction, the continuous variables. Okay, great. So let's go on. So here we go. And now we're going to we're getting closer and closer to doing the quantum algorithm here. But you see that the boundary map, when our chain complex is expressed in terms of abelian groups that are just these vector spaces, and then our boundary map is just a sparse linear operator on a 2 to the n dimensional space, which obeys dk minus 1 times dk is equal to 0, which is very easy to verify in the way that I define this. And so now, what is the goal of simplicial homology? Again, homology applies to any of these chain groups, and the simplicial homology has a particular geometric interpretation. But let's focus on that because it's possible to visualize in a reasonable fashion. So the original goal, as mapped out by Riemann and Betti in the 1860s. By the way, I gave a talk. The closely related talk to this at the Scuola Normale Superiore in Pisa last year, and they said, "Oh, Betti was the head of the Scuola Normale Superiore in Pisa." And in fact, apparently he was a big Italian patriot. He fought in the war against Austria for independence and the student brigade, and luckily he wasn't killed because most of his friends were. And then he and Riemann, it was interesting in their correspondence. I took a look at some of their correspondence. It was really interesting how much they were struggling. They were just struggling to try to understand what was going on. And it's salutary to go and look at these results, like Riemannian geometry, and think that we now accept. It's like, oh yeah, sure, but Riemann and then Betti and these guys, they were like, what the hell is going on? It's quite great. So yeah. So the goal that they came up was to find and count holes and voids at different dimensions. So here is a 2-dimensional hole in this complex right here. And they felt, oh, okay, a good way of, the 2 surfaces have a lot in common topologically if they have the same number of holes and voids in all different dimensions. So these are topological invariants, and it's a nice topological invariant for these systems. And so here we go. So here is the way that this works is pretty simple. This hole right here is bounded by the chain 1, 2, plus 2, 3, plus 3, 5, plus 5, 1. And the boundary of this chain is equal to 0 for just the same reason that I had another chain that was the boundary was 0. But this boundary of the hole is not the boundary of any 2 chain in the complex. There's really only one 2 chain in the complex. It's this 2 simplex 3, 4, 5, and that's not the boundary of the hole. And indeed, by its very definition, the boundary of the hole is the boundary of the hole, and it's not the boundary of some chain in the complex. That's the whole point. So so that means that the boundary of the hole is not equal to the 2 boundary map acting on some 2 chain in the complex. So the idea is we're looking for things that are boundary-less, but that are not themselves boundaries. And this was this idea that Riemann and Betti came up with, and that Poincaré later put into practice. Okay. Yeah, please.
or disk which is same as market to a sphere with a puncture, do you call this puncture as a hole in your previous slide?
Oh, like a disk with a puncture? Yeah, I think you probably have to in the sense that if you do Poincare, what Poincare did and, digitize or discretize this disk with a puncture, then the puncture would have to be like a little hole, like this two-dimensional disk would have to be a triangle, but that's something that's not in there. I don't know, somebody who knows more than this, Melanie, you know more than this than I do, yeah, I think that's how it would have to be. And then you'd have to like, if it's just a point like puncture, you'd have to take some kind of limit as the fineness of your discretization, as your discretization gets finer and finer and finer. Okay, another way of saying this is that the boundary map acting on this boundary of the whole gives 0. And also the transverse of the boundary of the two-dimensional boundary map is 0, because this says that this boundary is boundaryless, here, this hole right here. And then it's not the boundary of anything here, because the only two-dimensional thing that's bounded by this is this simplex right here. And so note that if this is true, then the square of this is also true. This little operator right here is in the literature, or at least in certain parts of literature, known as the Dirac operator, for reason that I'll mention in just a second. And if we square it, so d1 plus d2 transpose times d1 transpose plus d2, this is d1 transpose or d1 dagger. I'm sorry, I always write things as daggers because I'm a complex kind of guy, at least a quantum kind of a guy, and use the fact that d2 d1 is equal to 0 and d1 transpose times d2 transpose is equal to 0, then I get that this is equal to d1 transpose d1 plus d2 d2 transpose. Actually, these are daggers because we're operating in this complex space. And this is called the Laplacian or the Hodge Laplacian for one simplices. And this is called the Dirac operator because the Dirac operator in physics is the thing you square to get the Laplacian, which is the Klein-Gordon operator. So it's actually kind of a quirky. It's almost, I think it is almost kind of a joke actually that this is called the Dirac operator. It's the square root of the Laplacian. Okay, everybody good about that? So these are these entities that we're going to operate with. And so now we see that these k-dimensional boundaries of k plus 1 dimensional holes lie in the kernel of both the Dirac operator at dimension k and the Laplacian at dimension k. And these boundaries now are these chains. There's just sums of these states. These are called the representatives of the homology. And so you see if we can project out these boundaries of these holes and voids, find the particular ones, then we'll have found the boundaries of the holes and voids. And the total number of such holes and voids is just the dimension of this kernel. So it is the kernel both of the Dirac operator at dimension k and of the Laplacian, the Hodge Laplacian as it's called, with dimension k. And this is equal to the number of k plus 1 dimensional holes and voids. And this number, known as beta sub k, is a k Betti number, named after Betti. Yes, Andre.
How do you know that the kernel, like explain why the kernel one thing wasn't the other? Why do you have the other one as well? Why couldn't something be a 0 of the Laplacian, not the Dirac operator?
I think that I'm having trouble seeing that because the Laplacian is a positive operator, and this is the square of this Dirac operator. So I think that's good enough for you. If that's good enough for you, it's good enough for me. All right. Okay. So let me just recap, and we're in good shape, even though I started 5 minutes late, which is the MIT tradition anyway. And I know with Harvard people go more bright and early. I know this because when I was an undergraduate here, and by the way, Arthur was my undergraduate advisor in the physics department. And when I took quantum mechanics in this building, actually, though the rooms were a little more dingy back then, from Norman Ramsey, he insisted on having it at 8 o'clock in the morning. And then he'd turn up all the lights and show these transparencies, like a whole bunch of transparencies. I would immediately fall asleep, pretty, 8 o'clock in the morning on a Monday morning in a dark room. And this is actually kind of why I ended up doing what I do, because I never really kind of understood that quantum mechanics stuff, because I was asleep for much of the time when Ramsey was teaching it. So when I got to Cambridge on a Marshall Scholarship, I said, I'm going to study quantum mechanics, like do a master's in history and philosophy of quantum mechanics. Maybe I'll understand it better. And which I didn't, but it's okay. It's like, but it set me on thinking about quantum mechanics and information. So as a recap, the goal that Riemann and Betti set out, and that Poincaré and then subsequently Noether, Vittorius and Meyer, and then of course many other variations more recently, they said, let's find and count the holes in k-dimensional holes or k+1 dimensional holes in a multi-dimensional surface. And these are topological invariants, so this is a nice way of characterizing the surface. And then the work that really comes from, I think, really primarily developed by Noether et al. Is this means let's find the kernel of this Dirac operator and of this Hodge Laplacian and calculate the dimension of this kernel. And so this has taken a question which looks like it has not, it's like just completely about topology and geometry and stuff like that. And it mapped it into, by this discretization in terms of simplices, that Poincaré came up with, and then this cool method of finding the kernels of this Dirac operator and Hodge Laplacian. It just got mapped into a problem in linear algebra in a totally great fashion. And this is like the origin of algebraic topology, so far as I can understand from reading books on the topic. And so this is kind of one of the very seminal results in algebraic topology. And now, now we kind of see where quantum mechanics comes in, because quantum mechanics are really good at performing linear algebra on 2 to the n by 2 to the n sparse matrices. Indeed, they do it exponentially faster than classical computers. And by this mapping, figuring out how to map the members of our abelian groups into these quantum states in a high-dimensional Hilbert space, but over a small number of qubits. Then, once we can do that, we can actually bring in the power of quantum computers and do all this whole procedure of computing the homology exponentially faster. And this is what you want me to talk about. I'm on schedule. On time and under budget so far. But this is not to stop people from asking questions. These are good questions, so keep on asking questions. All right. So now let's be more specific about this. So through methods that I and others developed back in the 1990s and that have been since refined and improved upon. But if we have a 2 to the n by 2 to the n sparse matrix, which is essentially a operator acting on an n qubits, then there are standard techniques in quantum simulation that allow us to apply the following unitary transformations: e to the minus I d of t, e to the minus I L of t, because d and L are Hermitian matrices. I can treat them as Hamiltonians. And then if I have access to their entries in some appropriate fashion, and we'll discuss this later because this is a key aspect, then we can actually treat them as Hamiltonians and evolve them forward in time. So we can, we can treat them as Hamiltonians, we can evolve them forward in time. And moreover, in addition to that, when we do this very efficiently, so even though they're 2 to the n by 2 to the n matrices, we can do this in time polynomial in n. Because you can exponentiate these matrices in time logarithmic in the dimension of them, which is a crazy thing about quantum computers. And all that's actually going on here is that actually ordinary quantum dynamics does this all the time. You know, if I have n spins, which you can think of as n qubits, and they're interacting with each other locally, the state of these lives in a 2 to the n dimensional complex Hilbert space. And the time evolution of these systems naturally enacts these operators. So that's the whole secret of quantum computing, is kind of using the fact that quantum mechanics is already doing something on these very high dimensional Hilbert space. And the time evolution is of these unitary transformations. And then if you can massage the system in the right way, you can actually make it so that this D is just your Dirac operator and this L is just your Laplacian. Moreover, if you can do that, then you can actually also project an arbitrary state onto the eigenvectors of D and L, which recall these eigenvectors of D and L for the zero eigenvalue. These are the representatives of the homology. And we can estimate the corresponding eigenvalues. And I'll show how you do this in just a second because it's very cool. Most people in quantum computing know this as the quantum phase estimation algorithm. However, this quantum phase estimation is actually a kind of digitization of what I would think of as kind of the first quantum algorithm, which was developed by von Neumann, which uses continuous variables, which, as Arthur points out, then for me, that's looking under the headlamp. And let's see how this works. So this is actually are we going to project onto the eigenstates of the Dirac operator and the Hodge Laplacian? Well, suppose we have a Hermitian operator, and it's got eigenvectors and eigenvalues. We don't know what these eigenvectors are, and we don't know what these eigenvalues are. But we can apply this Hamiltonian. What von Neumann says is, what von Neumann says is join a continuous variable x, where it's like a pointer variable, and x is located at the state x equals 0 to begin with. And then take the Hamiltonian together with the momentum operator, and for not know about quantum mechanics, for continuous variables, the momentum operator is just I over h bar ddx, acting on the set of wave functions in x. And then what the momentum operator does, if you exponentiate it, is it translates this pointer variable, but it does so for each eigenvector. It translates the pointer variable by amount equal to the eigenvalue. So in fact, if I've got some arbitrary state, I don't know what the j's are, and I don't know what the eigenvalues are, then this method will actually correlate, or in fact entangle, the eigenvector with the corresponding eigenvalue. And so this register contains the corresponding eigenvector, and this vector contains the corresponding eigenvalue. And this is von Neumann's pointer variable model of what is famously called von Neumann measurement. And it's the last, if you doubt me, please look at the last chapter of this book, 1931. On the mathematical foundations of quantum mechanics, which I recently learned. In fact, von Neumann arrived, he did his PhD under Hilbert at Göttingen, and he arrived there in 1926 or 27, and quantum mechanics had just come in, and von Neumann apparently told Hilbert that he wanted to, work on the mathematics of quantum mechanics. And then he started, creating this whole apparatus of Hilbert spaces and von Neumann algebras, and which is tricky because the Hilbert spaces, the Schrödinger equation, are infinite dimensional. So there's all kinds of tricky stuff. And so he had actually worked all this stuff out as part of his PhD thesis. And his book, The Mathematical Foundations of Quantum Mechanics, essentially contained what he did in doing his PhD. It's kind of amazing. Yeah.
Curiosity, historical question, but what did people think of him at that time when he was working on this? Because I could imagine as a physicist, when you look at this at that time and be like, this is nonsense. Like, what kind of mathematics are you doing? It sounds like you're using like a bazooka to solve a problem.
Well, if you read the Mathematical Foundations of Quantum Mechanics, it is true that it's a bit dense. But you know, there were a lot of mathematically inclined people, like Pauli, for example, and Dirac, who were working on this at the same time. And, you know, once they got over, my personal fear of that book is reading these German Gothic variables, so all the variables are in these German Gothic letters, and I can never tell how many, you know, the M's, everything seems to have too many lines, like, and it's shaped in a weird way, and I can never remember which is which. Once you get over your fear of German Gothic variables, it's actually pretty, it's not straightforward, but you know, and he's very physically oriented. Von Neumann was a great mathematician, but he was a very practically oriented person. So when you read the quantum mechanics, it's like comes across well, and it's a great book. I highly recommend reading it. That's one of these books I had to read for when I was trying to learn quantum mechanics. So I was doing this MPhil history of philosophy of science, and it really helpful book to read. So I don't know how people treated it at the time, but I think von Neumann, I wonder how he was fit in at Göttingen, I don't know. But once he wrote this book and he was talking with Paul, there were not many people doing this then, right? So I mean, I think that he was accepted pretty well. Okay, so here's the thing. I mean, this von Neumann pointed variable model, which the digitized version is just the what's called the quantum phase estimation algorithm, allows you to project out to find eigenvalues and of permission operators, in our case, sparse, very high dimensional but sparse permission operators, and to project out the corresponding eigenvector. So this is what we need. So it's actually, in the end, it turned out the really hard part was actually just figuring out how to map this apparatus of homology onto the linear algebra of quantum mechanics. And after that, the tools just were there. So here's how our original algorithm worked. This is with Paolo Zanardi and Silvana Gonorani from 2016. We'll talk about variance. So the idea is you map k simplices. So this is like a k simplex that gets mapped to a quantum state. I give you two ways for doing it. These are all to be done efficiently on a quantum computer, given some description of the complex. And then we use this von Neumann pointer variable model or quantum phase estimation equivalently to project a uniform superposition of all the simplices in the complex onto the kernel of the Dirac operator and the Laplacian, Hodge Laplacian, which is the kernel. They have the same kernel.
So actually, just a question about DK and LK, because I'm not sure if I missed it. But if I were to actually implement this like on qubits, I would have to actually construct this Hamiltonian and like devise interactions between certain pairs of qubits. So how, in practice, how would I do this?
Yeah, so the way these you need a description of your simplicial complex that simply allows you to identify when a simplex is in the complex. So you have let's say an oracle that tells you the simplex is in the complex. Once you know a simplex is the complex, then you can construct the boundary operator because you know of all the faces. Once you know a simplex in terms of its vertices, then you know what all the faces of the simplex are. And you start at the beginning to set a particular order and ordering of the simplices, of the vertices, and then this allows you to keep the orientation of all your simplices throughout. So it isn't completely trivial. But the important thing is that you need, for these quantum simulation algorithms, the way that they work is given a row index, then you can then either calculate or you're given a way of where the non-zero entries in this row are and what those entries are. But for the boundary map, that's particularly simple because the non-zero entries are just at the simplices that correspond to the faces. The row index corresponds to a simplex, and these other indices just correspond to the faces, which you know what they are, and they just have terms plus or minus one. So everything is cool in terms of like fitting in with how you do these quantum simulations. Yeah.
What if the permission operator we care about is not sparse, like if we have?
Yeah, that would be bad, but it is sparse because like the largest simplices we can have are n simplices, and then there are just n faces.
So in a bad case, we will just stop using the complete estimation will just stop working.
Yeah, but it doesn't, we have a 2 to the n matrix, and there are at most n entries in any row. Well, and it's remission, so over any row or column. So it's sparse. It's sparse. Okay. All right. So if we successfully project, and by the way, with state preparation, you have to be careful about all these things. I recommend Sasha and my paper on this topic, which goes into it in category detail. I'll give the reference on the next slide. If you successfully project onto the 0 eigenvalue, recall that you, with phase estimation, you correlate the eigenvalue with the eigenvector. So after doing the von Neumann pointer variable operation or the phase estimation, and you find that this is x is equal to 0, then you project it onto the kernel of the Laplacian. And then you actually have a representative of the homology. You project it onto a chain that bounds some k plus 1 dimensional hole. So that gives you the representative of the homology in quantum mechanical form. And then the probability of success yields the dimension of the kernel, and that yields the Betti numbers. Of course, then you have to be very careful to figure out, how many times you have to do this to estimate the Betti numbers to a particular degree of accuracy, which I'll talk about on the next slide. But are people okay about this? Yeah,
I have 2 questions.
please.
The first is, you mentioned the implementation of checking, of whether or not a particular, let's say, basis state is the simplex of the complex with the use of or in general, those orbitals are probably extremely hard to produce, but is it easy to produce because the matrix is sparse?
I think actually the answer for that depends on how you're given the description of the complex, right? So the original work that we did with Paulo is we had a clique complex. So for data analysis, you're given the edges between, you're told where there are edges between vertices, and then you identify k plus 1 points as a simplex if the edges connecting all of those k plus 1 vertices are less than some distance, epsilon. Right? You take some scale, we say it's a simplex if that's less than that. Now that's an easy computation to do. But that doesn't mean that finding all the simplices here, for this, you actually have to find the simplices in the complex, and that's known to be a very hard problem because that's the max. So we know that this is going to fail on some places. I suggest you talk with Sasha about this because this is a specialty. But let me just actually give this, I'll just give the computational complexity. This is perhaps, we don't need this, I'm also running out of time. The point is that it's, for this original algorithm, it's polynomial in the number of qubits. It goes as n cubed. And then S sub k is the number of k simplices and then beta sub k is just the Betti number. And then delta is the multiplicative accuracy to which you estimate the Betti numbers. And rather than just the important things are, it's polylogarithmic in the dimension of the complex, which means it's exponentially faster than the best classical algorithm. That's the first part. You have multiplicative accuracy for this. It could be better, and actually more recent versions of this improve on this. I think you can get this down to n squared. I think you can get it to 1 over delta. Can you do better than this? I think you can get down to, you can remove the powers of 2 here. I think that's pretty much it. By various kind of, actually pretty standard techniques. Versus order 2 to the 2 to the n for the 2 to the 2n for the classical algorithm. Because the classical algorithm's got to, it's got to diagonalize a 2 to the n by 2 to the n sparse matrix, and you're just kind of stuck with those kinds of algorithms. Okay. And let's hear features, and we're almost done here, so we're actually kind of on time. So you can see that this works from the previous slide, that it works best when your Betti numbers are big. If your Betti numbers are eensy weensy, so like 1, which is what seems to be happening to us a bunch with this Khovanov homology, then this particular algorithm doesn't necessarily work very well. But so it works best when your simplicial complex looks like sourdough bread with a whole bunch of bubbles in it, large Betti numbers. I mentioned this possibility if the Betti numbers are small, and this is what we've been looking at with Sasha, Michelle, Alan, and Paolo. Maybe you can use thermalization or quantum annealing to find the kernel, because you can treat the Hodge Laplacian, it's a positive matrix, you treat it as a Hamiltonian, you try to cool it down and to find it to its ground state. And there are these very cool results, cool cooling results recently in quantum computing that show that these thermalization algorithms can be very effective. But unfortunately, we have no idea if they're actually effective here, but I will state that they can be effective and maybe this will work. So we don't expect this quantum algorithm to work in the worst case though, because finding the exact Betti numbers is sharp P hard, because you actually have to count the dimension of this kernel. And if you set up your simplicial complex in the right way, then this is counting the number of solutions to some NP complete problem. So you can, in the usual kinds of tricks, you can encode it. So counting these is that's sharp P is, sharp P hard problems are one where you have to count the solutions to some kind of problem in NP, and that's in general hard. And also finding these Betti numbers up to multiplicative error is also NP hard. I'll mention this is in our paper, Sasha and my paper on this, and some other papers on this. I'll mention these I'll put in references on the next page. But this is very widely applicable. So here we first tried applying this quantum data analysis. Actually, if we had just started from general homology, it would have been a lot easier, because the quantum data analysis, because here, as I mentioned, you start from just the edge lengths between different data points, and then you build your simplicial complex in this way. This is called a Vitoris-Rips complex. It's an example of a clique complex, and this makes things complicated. In particular, we have these issues like, max clique is a hard problem. However, if you're just given a list of simplices, right? So I like this one. This is the example that we came up with. This is Facebook groups. Facebook. If you say a simplex, a Facebook group is a simplex. And if there are k+1 people in the group, it's a k-simplex. And then that's it, right? Then this actually have all these overlapping groups, and subgroups are also simplices because they're subgroups. And so the Facebook data set of the connectivity is in fact a simplicial complex. And Facebook for sure has a list of all of its Facebook groups, including the identities of the people who are in that, plus for each person which Facebook groups they're in. And then you're okay, because you just it's not a max clique problem anymore. You just say, hey, Facebook, what's your largest Facebook group? And they'll say, aha, what's this one right here? Wonder what Facebook's largest Facebook group actually is. I'm not sure. I dread to think. Okay, so if you're given this kind of data, then actually all of this stuff goes through quite effectively. And so these kind of no-go theorems no longer necessarily hold for you. I don't have time now to talk about knot theory and Khovanov homology, but it's a really lovely set of ideas that allows you actually, as I think that Tom Roca, who's a friend of mine, he used to be the head of the math department at MIT, and we came in at the same time at MIT. You can use this to detect the unknot. You see where I made a knot, and this knot actually, you can look at it and say, hey, that's the unknot. And then there are other possibilities. We're actually getting more information than just the homology, because we're projecting onto all the eigenvectors of the Hodge Laplacian and getting their eigenvalues. And this gives you information about, like, Mark Katz's famous question of, can you hear the shape of a drum? Because this Hodge Laplacian, it's kind of like it's higher harmonics in this harmonic analysis. This higher harmonics, the higher order eigenvalues tell you got geometric information about this complex. And I have to say that we would love to have, anybody who knows about this stuff, let's come and talk with us, because we'd love to have some more information about this and possible applications. You read stuff in the literature, they say, yeah, there are lots of possible applications, but I don't know about all of them. So, and then I just think that's pretty much it. Let me give these variations. I gave the original paper. I didn't put that here. Sorry, the original paper is with Paolo Zanardi and me. If you look up Lloyd Zanardi topological, you'll find it. This is I recommend our paper together that was basically Sasha's master's thesis at Khovanov. And I recommend it because he wrote it very clearly. And I didn't screw it up too much by editing it. But he did his master's thesis, actually, it's from A to H, but he did it here with me as supervising it. And then there's a bunch of methods. These folks from IBM shows how you can use fermions to keep track of the signs. Makes sense if you remember the stuff about keeping the order of stuff, get these signs. That's actually cool. Ryu Hayakawa has refreshing simplifications in this paper, and then he just come up with some totally new cool stuff, which I do not yet understand in a recent paper. You can decrease the number of qubits. This is the Google group that did a very comprehensive analysis, and we spent a lot of time talking with them when we were about to publish this stuff. Many more. Oh yeah, here's this nice by Marco Coutinho and Tanya Kohler. They took this beautiful and very well-known paper by Ed Witten from 1985, something like that, from 1980s, that shows that if you look at the ground state of supersymmetric theory, the supersymmetry, for those of you who don't, I won't even describe what supersymmetry. For those of you who know what supersymmetry is, you know what it is. If you don't, I'm not going to describe it. It's thought to be the basis for superstring theory and for supergravity, etc. So if you look at the ground state, then perhaps not surprising, the ground state becomes this ground state, the kernel of a suitable simplicial Laplacian, and in these supersymmetric theories. And so you can show that this is all equivalent to finding the ground state of suitable supersymmetric field theory. These papers here, kind of ironically, they all got posted on the internet in the course of a few days because it turned out that there was kind of a 100 topological quantum monkeys thing where, it seemed that everybody was thinking about this, and all of a sudden it went from critical mass, and everybody published at once, and then we had a fun time trying to get everybody in line so that everybody was playing nice with each other, which in the end I believe that they did basically. Right. So I think that's it. I don't have anything more. That's it. Thanks very much.
Thank you very much for a very interesting and inspiring talk. There were a lot of questions, but maybe there's some more now.
Yeah. Oh yeah, we used if you're familiar with quantum phase estimation, it was developed by Kitaya. He didn't mention that it's actually the digitization of the quantum itself. And there's if you look at Nielsen and Schwab, you'll find these games. We used in addition for the there's a sneaky trick which Aram Harrow and I developed for proving quantum phase estimation using squeezed initial states, which gets you much better than, which gives you significantly better results than the standard way of doing it. But it's just really the standard version. I mean, that's one of the nice things about this is that the pieces that go into the quantum algorithm are really just quantum phase estimation, which is a very well-known algorithm, indeed in its von Neumann form, the very first quantum algorithm. And then these methods from quantum simulation, which are so if you look at the original version of that, this is this paper that I wrote in 1997, I think. 96, I don't remember. And that since then the scaling of those algorithms has been improved by quite a lot. Yeah, the fancy versions were done by Ike Chuang and collaborators recently, but I have to say that I was trying to verify these results and I got stuck in their paper. So,
many times people use computers to do mathematical proofs, and
Yeah.
then there's the question of the validity of the computation
right,
mathematically.
yeah.
With a quantum computer, what is the status of such things?
Yeah, that's a very good question. So it's not clear to me how, I think that, you know, if suppose if you project onto a particular boundary of a hole or void, if that's relatively small, then you can make measurements and you find the set of simplices that are bounding this hole or void. And then I believe from that you could verify that it is indeed a hole or void, but I'm not sure of that. Sasha, what have you thought about this? Not clear to me that these are easily verifiable classically.
This, I think, is like one of the most, I think you can do it efficiently, and it's one of the.
You can do it efficiently.
Yeah, one of the most promising areas for actually proving exponential quantum speedups. Because for these kind of things, verification things, you can show classical methods. Versus for the Betti number thing, it's hard to prove that actually the best classical algorithm takes exponential.
Right, that's right. That's right. Yeah. But I think that's a very good question. But why don't we talk about this and like let's people are working on this. We're going to start talking about this. I know that multiple group members are here, including former group members. So we're going to start talking about this on Thursday afternoons and try to see what we can hack together with it. There are a lot of good questions. You had a question.
Yeah, so you said Dirac operator is counting the number of holes that are themselves.
Yeah.
But in the definition, you add this to operator. Yeah, why? Like maybe they cancel out.
Yeah. That's let me go. I somehow seem to have lost it. Sorry. Sorry, what happened to my talk? It's right here.
I unshared your screen.
Oh, you unshared my screen. That's why. No wonder. Let's see if I can share my screen now. Oh, am I still on Zoom? The Zoom. Yeah, right. Yeah, great. Here we go. Share screen. Let me share it again. Okay, good. Yeah. Yeah, so this is the D1, the Dirac 1 operator. Yeah, it's a funny object. I mean, if you go read in the literature, people focus on this Laplacian. Because I mean, it's manifestly positive, and its kernel is the same as the Dirac operator. But it's more efficient. The Dirac operator is sparser than the Laplacian. And so it's more efficient to implement e to the minus dt than it is to implement e to the minus lt. If you want to do this cooling technique, you want to use e to the minus lt, but yeah.
Right, so you have like two conditions. One is that the other condition is that it's not bounded. These two are independent, right? But
Right.
add them together, maybe some of them are zero.
Yeah, maybe this is easier to look at in the Laplacian. So let's look at these two terms in Laplacian. I think you'll agree that if you're in the kernel of D1, then you're in the kernel of D. And if you're in the kernel of D2, dagger, you're also in the kernel of this part right here. So, and this part says, okay, it's boundaryless. And this part says, okay, it doesn't have a boundary. So in the Laplacian, it has to satisfy both of these conditions. for it to be the case. I think maybe you're saying it's not so obvious that when I add this together, it's gotta satisfy both of
I
these.
guess we just bear in mind that.
Yeah,
But the Dirac operator is not positive.
right.
And so if you flow with the Dirac operator, you're not going to be going to the zero, you'll go somewhere else.
If you flow with the direct operator.
You said e to the minus.
Yeah, if you try to, right, if you try to cool it down, then that's not clear what you're trying to do. But, you know, D1 dagger is equal to L1, and it's not true in general, right? But it's from this feature that D1 dagger, I'm sorry, that D2 D1 is equal to 0, and D1 dagger, D2 dagger is equal to 0, so that makes this work. I believe that, does that help with your question?
I think another easy answer is that both the terms in the Laplacian are positive definite by itself. So if something is in the kernel of L, it's in the kernel of both terms. Both conditions are satisfied.
Yeah, it's a positive operator, if you, the sum and a positive operator, if you have two positive terms, then, and you're in the kernel of the overall operator, you have to be in the kernel of both of these at the same time.
Perhaps we should ask if there are any online
Yes,
questions.
good question. You wanna look? Pop them in the chat, or like, just like say
Oh,
something.
There is a question in the chat.
Let's try that. Okay. Oh, yes.
Wei has a comment. Maybe you'd like to say something.
Yeah, I'm missing the first line of your comment. Oh, here we go. The time evolution algorithm, sorry, Wei says, nice connection. Some comments, the time evolution algorithm may be more expensive than the direct diagonalization of the Laplacian operators. Right. Sorry. Order n cubed. For Hodge Laplacians, we need to deal with manifolds with boundary and counter boundary condition complications. For Khovanov homology, the computation can be very extensive. Boy, do we know that. Aaron Lauda bought these, like a whole bunch of new computers to put in his office at USC. And then he also had to up the air conditioning because the computation was so extensive with the Khovanov homology. Yeah, I agree with that. But actually, I think that the diagonalizing the Laplacian directly classically doesn't take time order n cubed. It takes time order 2 to the 3n, 2 to the n cubed. It's the dimension of the operator, not the number of qubits. So the direct diagonalization classically is exponentially slower. I actually think if you try to do it, because if you try to do, it would be faster if you try just find the ground state sector of the Laplacian by conjugate gradient descent. And I think that will bring it down to n squared, to 2 to the n, 2 to the 2n, which I think was what I actually quoted in as the classical part. Did that help Wu Wei?
Yes, thank you. Yeah.
Okay, great. Other questions? Yes.
So you had mentioned at the end that computing exact Betti numbers is sharp. But
Yeah.
do we know that there doesn't exist a polynomial time operator that just like delta approximates a Betti number?
Yeah, I don't think, yeah, go ahead.
Well,
Sasha knows.
Depends on what approximation. If you target a multiplicative approximation, then we prove in the same paper that that's NP height.
Yeah.
So also probably bounds. If you want an additive approximation, it's an open question.
Yeah. Of course, it's an open question whether solving a short p-hard problem is actually hard. Sad commentary on computer science. Yeah.
So you mentioned as one of the applications, topological data analysis.
Yeah.
So in that context, there's several stages. One is where you first have your raw data.
Yeah.
Some metric that allows
Yeah.
you to compute distances between things and construct the Riemann-Roch complex.
Yes.
And then there's a second part, which is computing the Betti numbers and the persistent
Homology.
diagrams.
Yeah.
You focused on the second half, right, in this talk?
Yes.
And for the first half, it seemed like you were suggesting it's very difficult to actually prepare your states and construct the associated complex from that.
Yeah. Yeah, if you look at our paper, which is in Nature Communications, it goes into this in detail. But right, because this Vittorius-Rips complex, as I described before, is a complex you get by giving edge lengths, and then you call k+1 points a simplex if the distances between them are all less than some scale. And so what you do is you set the scale. In persistent homology, what you do is you set the scale, you calculate the homology, and then you change the scale, so you make it bigger, which means you're grouping more things together, and you calculate the homology again. And you look for, what you're looking for are things like holes and voids that persist as you make things, group things more and more together. Eventually, once you make the scale that you're grouping things large enough, all these holes and voids will go away. But the idea is that real features of the data are those that persist over many grouping scales. This is a result that's ascribed, I believe, to Karsten Nielsen at UC San Diego. But when I gave a talk on this at UCS Santa Barbara, when the paper came out, almost 10 years ago, Michael Friedman got super excited, and he ran to his office and he brought back this set of documents that said like top secret on it. And he said, I figured out all these things for a dark top secret, government program. And then I discussed it with people, and then Karsten Nielsen then published it. So he wanted to he showed me these top secret diagrams. Probably be put in jail for that. But yeah. So it's a very powerful technique, and actually, people. One group of people that uses this persistent homology are people in finance, right? Because you basically have this very high dimensional set, which is a set of time series for like huge number of different prices for things. And then it sits in a very high dimensional space. And then you just try to estimate aspects of its topology. And you don't have to get everything, right? But if you get some aspects of its topology, and then you're monitoring the topology of these time sequences as something goes on, and all of a sudden the topology changes, that means something's going on, right? So they use it as kind of like a detector for the market's about to crash or something like that. And this is actually used by folks like these people, Goldman Sachs, were interested in doing this. So it's a pretty widely available problem. But this you're not going to find like the max cleave. There's different problems associated with that. Why don't we talk about it offline? Okay. Because it's like a complex set of documents.
No. I think we've had a lot of inspiration. We have to have you come back again with some more results. Thank you so much, Seth.
There's an homology paper out there.
Thank you.
Thank you.
Bye-bye.